For years, the story of AI progress seemed, well, pretty simple, right? Just get bigger. Bigger models, bigger data centers, bigger budgets. But the real story, the one that actually matters, isn't about size at all. It's about physics. Today, we're going to unpack the predictable physical laws that govern the rise of these massive AI models and the very real walls they eventually ran into. So we've covered some huge ground. We tackled two of the most fundamental bottlenecks you can imagine. We solved for latency, that's the problem of waiting in time, and then we solved for bandwidth, literally widening the pipe in space to shove massive amounts of data through. These were absolutely crucial engineering wins, and they set the stage for what came next.
But getting those things right just left this one giant question hanging in the air. It wasn't just about how we could build these enormous systems anymore. The real mystery was why it kept working. Why did just adding more silicon, more hardware, lead to predictably better results? Was it all just a lucky guess, a shot in the dark? Or was there something more fundamental going on?
To get to the real answer, we first have to talk about the story everyone thinks they know. It's a simple narrative, and spoiler alert, it's the wrong one.
Oh, I'm sure you've seen the headlines. AI gets bigger. More parameters means it's smarter. Just scale it up, it'll solve everything. This whole narrative made it sound like a digital gold rush, where companies were just gambling on size, hoping that if they made things big enough, intelligence would just magically appear.
Look, it makes for a great headline, a great story, but it's fundamentally not what was happening. This progress wasn't a gamble. It was a calculated, engineering-driven process, all based on a single metric that honestly has nothing to do with being smarter. All right, let's get into the real stuff. The one metric that engineers actually obsess over to track progress. It isn't intelligence or understanding or any of that. It's much, much simpler. It's just math. That key metric is called prediction error, or most of the time just loss. It's just a number, a score that quantifies exactly how wrong a model's prediction is. So if a model's trying to guess the next word in the sentence, the loss measures the distance between its guess and the actual word. The entire goal of training is just to make that number as tiny as possible. And this right here, this is the crucial distinction. Lowering that loss score makes the model a better predictor. It gets more accurate at guessing the next token. That is all it means. It does not imply the model understands language in any human sense. Progress in AI is not about creating a mind. It's about minimizing a mathematical error function. This relentless focus on crushing the error score led to one of the most important discoveries in modern AI. Because when researchers started to systematically plot their progress, they didn't see chaos. They saw a pattern that was just shockingly predictable. So when researchers graphed the prediction error against the amount of compute they threw at the problem, they saw something remarkable. On a special kind of graph, a log-log plot, the data points didn't form some random cloud. No. They formed a nearly perfect straight line sloping downwards. A straight line like that means something very specific. It's called a power law. It's a concept straight out of physics that describes a predictable lockstep relationship. For AI, this was a total game changer. It meant that for a given increase in compute, you could reliably predict the corresponding drop in your error. This wasn't just a trend, it was behaving like a physical law. And this is it. This is the core idea. Scaling worked because prediction error followed a law, not a trend. Companies weren't just guessing that bigger models would be better. The math was telling them exactly how much better they would be, and exactly how much it would cost to get there. This discovery turned AI development into a rigorous engineering discipline overnight. Scaling wasn't about making one thing bigger anymore. It was a precise, multivariable balancing act. To keep that error rate marching down that nice, straight line, you couldn't just pull one lever. You had to pull three, all in harmony. The model size, which is measured in parameters, the training data measured in tokens, and of course, the raw computational power measured in flops. And these three were completely intertwined. If you just increased the model size, but you didn't add enough data or enough compute, that beautiful power law would break. The prediction error would just flatline. You'd be wasting a ton of resources. So effective scaling was all about finding the optimal ratio between these three things. So for a few years, this balanced scaling drove some absolutely incredible progress. But like any physical law, it has boundaries. And in 2022, researchers discovered a critical guardrail. What they realized was that the industry's standard ratios were just off. The focus for so long had been on scaling up the model's size, the number of parameters, as the primary thing. But it turned out that many of the largest models were actually computationally inefficient. They were being undertrained on too little data. This discovery led to the Chinchilla scaling laws, which is basically a revised recipe for optimal performance. It showed that for every parameter you add to a model, you have to add a proportional amount of training data right along with it. The key insight was that data was at least as important as model size, if not more so. And this exposed the ultimate constraint. The power law works, but only if you can keep feeding it the right ingredients. And that means scaling as a strategy has a hard limit. It fails when you run out of high-quality data. So, what does this all mean for AI today? Why does this shift from this simple bigger is better story to one of physical laws and real constraints actually matter? Well, it explains why the whole field seems to be moving with a bit more caution now. It's not because innovation has stalled. It's because the industry has matured. It's moved from that brute force scaling phase into a new one that's constrained by the physics of the system itself, namely the finite supply of high-quality data. The era of just making things bigger and hoping for the best is over. And this brings us to the central theme. Scaling is an engineering discipline, governed by predictable laws and bounded by real-world constraints. It is not, and it never was, a gamble. Let's just quickly summarize what we've really learned. The progress of large AI models wasn't magic. It was driven by the discovery that prediction error follows a predictable power law. That law only holds when you scale compute, data, and model size in balance. The ultimate ceiling on this progress is the availability of high-quality data. And finally, scaling is a process with very real limits, not some myth of infinite growth. So large AI models didn't succeed by accident. They succeeded because they followed a predictable physical law. Bigger models worked because the math said they would. They hit a wall when reality, the hard limits of data and efficiency, pushed back. This closes one chapter of AI development, and it opens a whole new one. Join us next time as we explore what happens when scaling alone is no longer enough.